All right. Thank you. Yeah, it's always a pleasure. And I'm excited to talk today about something that I haven't talked about in a while, about platinum CH activation chemistry. Um, and so I'll first do a little intro. And a lot of this work, like I said, goes back to my PhD thesis. But that I think it's a good kind of, we're going to cover some of that as a way of setting up kind of what I'm doing now, but also thinking about things that we can learn about platinum chemistry. And so there'll be kind of two parts to that. There's of course there's tons of stuff that I don't have time to talk about. There's some really cool hydrolation chemistry that I did a little bit of that I won't be able to talk about. But mainly this is going to be on platinum CH activation from platinum 2 compounds. So a little bit about me. I'm from Bainbridge Island, Washington, which is right next to Seattle. So I did my PhD with Dr. Karen Goldberg at the University of Washington. She's now at University of Pennsylvania. And then I did so organometallic platinum chemistry there that I'll be talking about. And I did a postdoc on involved CO2 reduction, and then started my independent career in 2013. So I'm an organometallic inorganic chemist by training. Depaul is a primarily undergraduate institution, so it's PUI. We've got two main campuses in Chicago. So there's one downtown Chicago called the Loop, and then there's one in Lincoln Park campus, and that's where my lab is. Lincoln Park campus is where the science faculty are. So we're the Department of Chemistry and Biochemistry. We have undergraduate degrees, bachelor degrees, and we have master's degrees, a small master's program. We do a lot of research for being a PUI, so we have about 14 research active faculty. And of course, I'm always happy to have visitors as we get back in person next fall. I think we're going to be fully back face to face. So working at a PUI is fun, but it's a different thing than what you might have experienced as a postdoc or a grad student, in that you don't have PhD students, you generally don't have postdocs. So things are at a slower pace, and you have to balance it with your teaching, which is usually your major focus. And so I do a lot of collaboration to keep things going. And again, Discord is a great way of staying connected, and Open Science Presentations has a Discord that's a great way to kind of stay connected with people and bounce ideas off of people. So these kind of social media tools have been great for me in my independent career. So for example, inorganic chemistry also have a teaching kind of website that's an organization called Ionic, and the website's called Viper, that's for virtual inorganic pedagogical electronic resource, so teaching materials we can share and use, as well as research ideas. And then I've also done some kind of online discussions. And so these ways of staying connected, even if you can't physically visit, are a great way of collaborating and networking, especially if you're at a PUI. So what does my lab do? I've already given a talk, like Dr. Meakin said a while ago, on my kind of bioinorganic chemistry. And CO2 chemistry really takes up a lot of my research area, and I've talked about that in a few different places, but I wanted to talk about some platinum chemistry that I haven't talked about in a while, and I haven't thought about in a while because I've been doing lots of CO2 chemistry recently. So we're going to talk about platinum chemistry. So, of course, there's always a motivation. Now, I'm not an engineer, unfortunately, so we're not, this chemistry certainly won't be solving the problem, but our motivation is that right now we get everything from petroleum and natural gas. We do lots of steps to get functionalized materials. There's cracking, distillation, various other reactions, right? And we get plastics and pharmaceutical stuff, right? And so petroleum and natural gas, hopefully we'll move away from all of that as a fuel, but we'll still need to use them as sources of functionalized chemicals. So there's lots of technology out there, but some of it is non-ideal in terms of the number of steps and energy involved. So for example, right now we get methanol from steam reformation of methane or coal to get mixtures of CO and hydrogen. Then you have to do a different catalytic system to make your methanol. And so as you get a bottle of methanol, that's where that's from, coal or natural gas. It'd be great if you could just take natural gas in one step to get methanol directly, instead of having to do multi-steps that can have waste and heat loss and energy loss, etc. I won't be talking about this, but there's also other things you could do. So for example, alkyl benzenes are used in things like surfactants, lubricants, precursors to things, and we can make them with Friedel-Crafts type chemistry, but it's usually anti-Markovnikov. Markovnikov selectivity, and it'd be great if we could do the linear versions, which are usually less selective. And so there's some platinum chemistry that has shown some benefits here, but I won't talk about that. And then one area that we've been thinking about a lot is alkane functionalization. So, if you take an alkane and you just crack it over a catalyst at high temperature, you're generally going to make the most stable product, which is usually an internal alkene. But we know that, if you take OChem, terminal alkenes, you can do all sorts of useful things with, right? And often it's, this selectivity would be great if you could do that. And there is some platinum chemistry that can do that. So really, it'd be great if we could improve the selectivity and efficiency of these processes for taking crude hydrocarbons into functionalized products. So our inspiration then comes from the fact that this can be done with platinum. So the original report is from the 70s from Shilov in Russia, and so he found that methane in water can be turned into methanol, which is pretty cool. Decent temperature, and involves a platinum-2 catalyst. And so there's 3 steps in the catalytic cycle. You have a homogeneous platinum-2. Platinum-2 is usually square planar, D8, and D8 things like to be square planar, 16 electrons in terms of the 18 electron rule counting. So platinum-2 is compound, and that does CH activation to make a platinum-2 methyl. So CH activation involves breaking a CH bond and making a new platinum-carbon bond. Now, this compound is fairly stable, but if you oxidize it to platinum-4, you can then do product release to release methanol by doing basically a nucleophilic attack with water. The problem here was that you're using platinum as a stoichiometric oxidant, which is about the most expensive oxidant you could think of. And also platinum decomposes over time, so your catalyst shuts down. So this isn't commercially viable, but it's an interesting idea. And this has caused, this was like the original report and has led to tons and tons of research in all sorts of areas. So an example of an improved system is the Periana system. So Periana and coworkers, they found that in fuming sulfuric acid, basically, acidically, they could take this platinum-2 complex and it would oxidize methane to a protected methanol using the sulfuric acid, or SO3, basically, as the oxidant. And again, you're using a platinum catalyst, so you do CH activation, but now your oxidation is a much cheaper oxidant, so that's great. And then there's product release, but there's no water in there because it's fuming sulfuric, so the nucleophile is now sulfuric acid, and you make this protected thing. So that's great, but it's inhibited by water, which you make, and you have to deprotect your product. So this isn't, again, probably not a commercial way of making methanol from methane, but it's good evidence. So again, there's improvements have been made, other metals have been used, but we're going to focus on platinum for this work. So that's this kind of general cycle is pretty commonly talked about. 1, 2, 3 here. Okay, so what people have done since then is basically studying each of these steps in detail. And so what you can do is you can do CH activation of alkanes using a platinum-2 complex that's been coordinated by nitrogen ligands. So you'll notice here, this is what's called a NAC-NAC ligand. This is a tris-perazyl borate. Here's another nitrogen thing. These are called diimines and amines. And there's lots of work in this area. There's a great review from 2005 and another good review from 2017. And the general way is you need to have an open site for the alkane to bind. So that CH bond needs to come in and displace the ligand and bind. And then you can break that bond either by oxidative addition or sigma bond metathesis. And often what we'll use is a methane product to be able to observe the CH activation. So for example, if your HR here is deuterated, you would make methane D, which you could observe by NMR. And then you can make your product. So that's the CH activation step at platinum-2. Now the oxidation step, people have been trying to do this with cheaper and cheaper oxidants, and the cheapest oxidant would be air. right? And so people have found that some of these platinum complexes react with air. So for example, platinum-2 complexes with dimethyls, right? You make these independently. With oxygen and methanol, you can make platinum-4 species, so it's oxidized. And this works with these, again, nitrogen-type ligands. And some people have been able to actually couple this together and get product formation. So Vedernikov and coworkers, and I'm sure there have been some more papers since this original report. So really tuning that system, you can get oxygen to work for oxidizing these things. So again, this is a classic chemistry approach. You just study like one little part of a catalytic cycle and really try to understand what's going on. So that can be done with oxygen. And then the product formation has been studied a lot. So when I was in Karen Goldberg's lab, this was a big area of her group, and she'd studied phosphine coordinated species with a variety of X type things. So this could be hydroxide, this could be acetate, all sorts of things. It doesn't have to be this type of phosphine. There are lots of work. Nancy Williams was her first grad student and had done a lot of work on these types of things. And this general scheme became apparent from a wide variety of reactions, where if you have a platinum-4, it's usually octahedral. It's in equilibrium with a platinum-4 5-coordinate species. And then from there, you have two competing reactions. So this intermediate is unfavored, and so it's made transiently. And so lots of kinetics were involved in sorting this out. You can do nucleophilic attack on the methyl and make methyl X. And so that's how you make methanol. But you also have direct CC coupling in competition, and you make ethane, and the X stays on there. So this is a really interesting way, because you see two different types of reductive elimination happening from the same compound. And then you can modify the conditions to favor one or the other. So for example, you can add excess X, and you'll favor the CX reductive elimination. You can add something that will bind your X or remove it from solution, like a Lewis acid, for example, and it'll favor the CC formation. So people haven't isolated these 5-coordinate intermediates, but they've isolated 5-coordinate platinum 4s before. And so we wrote a review in Topics of Organometallic Chemistry about this. And surprisingly, there haven't really been any that many new platinum 4 or 5-coordinates since then. But they have a lot of really cool reactivity, and they do CH activation often. So there's some really interesting chemistry there. So what I was working on in general in my PhD was, okay, we know that we've got these 3 different areas pretty well studied, right? CH activation at nitrogen ligands, oxidation at nitrogen ligands, and then reductive elimination well studied at phosphine ligands. So the idea was, well, can we get one system to do all of these, right? So can we maybe mix phosphine and other type ligands in there to do CH activation? And so that's the biggest problem, because CH activation had really only been seen at nitrogen-based ligands. So that was one of the first things I tried to tackle. And so before I go any further, a few things about platinum complexes. So again, platinum-2 is square planar. It's usually, there have been some 5-coordinate platinum-2, but generally it's square planar. And if you have a phosphine ligand, you can use phosphorus NMR. But platinum is also spin active. One of its isotopes is about 33% abundant, and it's got a spin of 1/2. So instead of getting one signal in your phosphorus NMR for your one phosphine, you get one signal and what we call these beautiful platinum satellites. Now, the distance between those satellites in hertz is a coupling constant, and it's a really large number, like thousands of hertz. But it's really, really characteristic for the identity of your compound, and also what's trans to your phosphorus ligand, and also the oxidation state. So it's really, really useful. In proton NMR, you also see the coupling to platinum and to the phosphorus. So this is a platinum methyl in the proton NMR. It's a doublet with these platinum satellites. And so the doublet is due to the phosphorus coupling, right? Phosphorus is 100% abundant, so the NMR splits a singlet into a doublet. But then you've got the platinum satellites, which are due to the 33% platinum character. So again, NMR is great for these. Platinum-2 is also diamagnetic, so there's no unpaired electrons, so it's great for NMR. So I did lots and lots of NMR in my PhD, and also in my work now. So here's some of the stuff we tried to do to try to get CH activation at phosphines. So I'm going to apologize for the chem draws because it turned out that moving from one computer to another caused some graininess, but so be it. And this is, if you've worked with phosphines before, you know they're smelly. They're also very air sensitive, or can be very air sensitive. So these phosphines turn out to not be air sensitive, which is fantastic. And that's due to their steric bulk and also the electronics. And so you can actually recrystallize this reindeer phosphine in methanol on the bench in dry ice, and it's beautiful white powder. So again, we kind of independently make platinum methyl species by using this platinum methyl starting material, and it actually does CH activation at room temperature, but it does itself, so it breaks the PC bond. But then we can isolate these species, and they're fairly stable. And again, you can get nice platinum phosphorus coupling in the phosphorus NMR that tells you it's trans to methyl at platinum 2. And we made a similar molecule here. It's always great when you get a crystal structure, right? So we solve the structures and to figure out, yes, we do have these square planar platinum 2s with a methyl on them. And again, we published this in Inorganica Chimica Acta. So I then was trying to do CH activation with these because phosphine ligated platinum complexes generally don't do CH activation. And instead of looking at alkanes, we tried benzene because that's actually more well known for CH activation. So the way you study this is you make the compound, you heat it up in C6D6 at some temperature, and you look for methane D in a sealed NMR tube. So methane's a gas, but it goes into headspace. But if your tube is sealed, it will go back in solution, and you can observe these gases dissolved in solution. And methane D has a very specific signal due to the deuterium, so you can tell if it's formed or not. So sure enough, it works. We can do CH activation of benzene, and we can see that it's trans to the phosphorus due to the coupling, and not to the carbon, right? And it works for both of them, which is great. So this is a fairly rare example of CH activation of a solvent or a free hydrocarbon by platinum. The mechanism for this is likely involving losing that dimethyl sulfide neutral ligand and displacing it. Again, you have to bind your substrate before breaking that CH bond. And so the way that we could kind of get some evidence for this is doing the reaction again, but in the presence of excess dimethyl sulfide, which is a liquid, a smelly liquid, unfortunately. And so it slows it down if you have excess dimethyl sulfide in there, because you have to knock the dimethyl sulfide off to get your substrate in. So that makes sense. And so for this, we are showing, yes, we can do CH activation with phosphines, but we weren't able to see alkane CH activation, unfortunately, with this system. So next, we want to move on to oxidation, or try a different system similar, and look at the oxidation and CH activation as well. So we moved on to maybe seeing if we could do nitrogen incorporation. So we made this kind of half and half ligand. You can think of this as like a mix between a diphosphine and a dipyridine ligand. It's easily made, but it's air sensitive, so you do this in the box. You lithiate and then add a chlorophosphine. And again, we put the platinum on it, the platinum methyls on it, and made this nice stable molecule. Got crystal structure, NMR. You can see if you've got different platinum hydride coupling, hydrogen couplings for the methyls, because one is trans to the phosphorus, which is your bigger coupling, and one is cis, which is your smaller coupling. And so you get bigger coupling transes, you can identify which methyl is which based on platinum phosphine coupling, which is cool. Unfortunately, this didn't do any CH activation, but we could get rid of the methyls by adding a strong acid and protonating them off. And you can see here that the methyl trans to the phosphorus was the more basic methyl that came off as methane, as opposed to trans to nitrogen. And we could tell that again by phosphorus coupling. So huge phosphorus coupling, because now this triflate is a weaker trans donor or weaker bound donor. Now, unfortunately, both of these complexes, heated alkanes or arenes, didn't do CH activation. So I had an undergrad at the time who is now has got his PhD, and he and I were decided to say, well, what if we gave it an internal acid? And so we decided to make an amino arm where this NH should now be somewhat acidic and might act as an internal acid, but also an internal base when it's deprotonated. And again, we made the same compound, except now we've got an NH here. And it worked well. they have similar structures, right? So you get crystal structures to confirm that they're square planar platinum 2. You have one methyl trans to the phosphorus and one trans to the nitrogen. Those have different lengths. They're bulky butyl groups, and then your pyridine rings. And we were able to show that NH was acidic. So we could deprotonate it with a really strong base, potassium hydride, and make the 18 crown 6 salt. We could also heat this in benzene, and we did indeed see a small percentage of CH activation. We saw deuterium incorporated into this NH. So that deuterium has to come from the solvent. So that's evidence for the NH acting as a acid and a base. The acid to make methane, and then the base to pull the D off of the C6D6. And so we saw some methane and some methane D. Now, again, we wanted to show with evidence that NH is involved, and it's not just transiently involved. So we did a few things. First, you can do Hg scrambling, and this shows that that's somewhat acidic, and you can exchange the or the nitrogen is basic, right? You can exchange the D for the H for a D. And then if you heat that, you see methane and methane D, but so we can do it with the H here or the D here. And indeed, with the deuterium there, we see a higher amount of methane D, showing that yes, it's acting as an acid to protonate off the methane. So yeah, there's definitely involved. This was an example of what's called ligand non-innocence. The ligand is involved in the chemistry. It's not just coordinating and affecting the metal. So we did that. It works, right? But we were also able to trap the intermediate, right? A species where they had protonated off the NH by adding a suitable ligand that could bind strongly. And so if you add pyridine, you can actually isolate the deprotonated species where it's lost the NH yet, but it hasn't done the CH activation yet. And we were able to again, show that with the crystal structure and show that indeed, we don't have the NH, we've got the pyridine bound. And the platinum phosphorus coupling also is consistent with the phosphorus bound to a weaker ligand than a methyl, right? So again, NMR is fantastic for platinum 2 complexes. If you have alkyls, especially if you also have phosphines. Phosphorus NMR is pretty quick. It's much quicker than carbon. It's a little slower than proton, but not by much. So these are not challenging experiments or time-intensive experiments to do, which is great. So again, we can do some CH activation. Again, we still couldn't get the alkane CH activation to happen. We could trap this, again, trap it with other ligands. So if you use a phosphine, you could trap it. If you just add a base that's bulky, it won't bind, right? Diisopropylethylamine is a strong, bulky base. And so that kind of doesn't get involved because it's too bulky to bind, right? So again, we were able to show that, yeah, we can get some CH activation at phosphine-bound species. So again, kind of summarizing this metal ligand cooperativity is this CH here is not acidic enough to come off easily, whereas the NH is acidic enough to come off easily, and we've been able to trap this intermediate, and then it can act, the deprotonated nitrogen can act as a base to be the source of the CH or CD that comes off when you break a CH or CD bond. So that's cool, right? This is, we're adding to the examples of non-nitrogen CH activation examples. Okay, so we can do CH activation with PX type things. The problem being that, we weren't getting alkane CH activation, but, we've got something that's worth. So next thing is we're curious about is what's with the oxidation. So we want to be able to oxidize this to platinum 4 to do product release, right? Can we do the oxidation if we swap in phosphorus for nitrogen? Because again, this has only been known with diamine or N2 type donor ligands, bidentate nitrogen donors. And so again, this is well known, the oxidation with its nitrogens, but the corresponding phosphine compounds, like if you have like a diphenylphosphinoethane, those are air stable. You can keep them on the bench, they're fine. So, right, what happens if we mix and match? And interestingly, we were able to taking back this compound that we made again, All right, so we didn't do CH activation, but let's see if it can react with oxygen. And so we react with oxygen in hydrocarbon solvents. So if you think back, the other ones reacted with in methanol. So we were just trying like straight up, does it react with oxygen? And we did see a reaction. And again, we can use phosphorus NMR to tell that the reaction happened trans to the phosphorus. So something's happening trans to the phosphorus. And this species formed pretty cleanly in decent yields. It still has one platinum methyl in there. You can see the platinum coupling. And there's a new methyl signal. It's CH3 group integrates, but there's no coupling for the CH3 to platinum or phosphorus, meaning it's further away, right? Coupling is distance dependent through bonds. So something's going on. We're making something, but I'm not sure what that is. It does react with oxygen. So we were able to get a crystal structure of this thing. And what had happened is O2 had completely inserted into the platinum methyl bond. So here's the starting material, and here's the product, OO carbon. So we've made a methyl peroxo species from a platinum methyl. That was unexpected, I think. We didn't know that that's what was going to happen. And it works in non-polar solvents like, non-product solvents like DCM or benzene. Yeah, so that was cool. And at the time, this was a very rare example of this type of O2 insertion into platinum stuff. You see some O2 insertion into like methyl radicals or like alkyl radicals, main group species that can form radical alkyl species. So what's going on? Well, we did a few control experiments. So if you take the two tubes and they're the same compound and solution, and you wrap one in tinfoil and another one not, you put them next to each other, this reaction goes at room temperature, but it goes slower in the absence of light. We can also add a radical inhibitor, BHT. All right, this is actually a butyrated hydroxyl toluene. It's a preservative, and that's a known radical inhibitor, and that slows the reaction down. So that's evidence for radical chemistry. We could also speed it up with AIBN, which is a radical initiator used in things like radical polymerizations. And so this all points to it being a radical mechanism. We tried some kinetics. Radical kinetics are not fun. They're rarely reproducible enough to get good data, and so I was unable to get reproducible kinetics. But we were able to publish this work as a pretty interesting new reaction. Now I'm not an expert in kinetics, and there are better people. So Luc Boisvert was a postdoc in Karen's lab, and he and Susan Hansen, who was a grad student, were working on this, and another previous work from a postdoc as well. They'd found that another example of O2 insertion. And so through lots and lots of kinetics works where they were able to get some reproducible data, they sorted out this mechanism. So if you take the palladium dimethyl BP compound here, exposed to oxygen, you'll get the peroxo. The way they figured this out to work was a radical chain mechanism. So I'm going to skip the initiation of the chain, but you can initiate with AIBN. But you make methyl radicals. They spontaneously react with O2 to make methyl peroxy radicals. That methyl peroxy radical can then react with palladium-2 to make a formerly palladium-3 complex. Now, this wasn't observed, but again, this kinetics bears this out. And then that species can expel the methyl radical, which then continues the chain. And so you insert O2, make methyl peroxy, back onto another palladium, spit out another methyl, and et cetera. And so that's the overall process to do this. And then there's a radical termination at the end, either two methyl peroxies coming together or something similar, right? So they were able to do lots and lots of very painful kinetics to get that information out. And so they were able to see that similar radical processes can be done at platinum and palladium chemistry. So that's really interesting. And at around the same time, in fact, I remember Luke coming back from a conference saying, somebody else is doing this too. And Bertovsek and coworkers had figured out this platinum methyl species inserted oxygen, but they needed that the actual complex can photosensitize. And they think they've done studies with palladium too now. And there's been other people who've continued on since then. But they were also able to observe the methyl peroxo species. So this type of reactivity was not something that had been really thought of before for platinum and palladium type chemistry. And so you can kind of think of an alternative potential catalytic cycle where you do CH activation, and then you do oxygen insertion instead of oxidation to platinum 4. And then somehow release your product. You could make a alkyl peroxo, which could then oxidize something, right, or be converted to an alcohol. So this was kind of the paradigm that we came up with after working through my PhD, where we looked at each of these processes individually. So that's kind of the setup for what I want to talk about next, which is, so I did my PhD, and then I went and did CO2 reduction chemistry for my postdoc. Very different, still organometallic. I learned electrochemistry, IR, infrared spectral electrochemistry, etc. So when I came back to Depaul, as you saw, I had came to Depaul as my independent career, I had 3 areas: CO2 reduction, bioinorganic, and platinum chemistry. And I wanted to do some CH activation chemistry, right? And so Depaul's a PUI, so I knew that I had to be more selective about how I approach the chemistry, because students can come in here and there for small amounts of time, and then then they got to go to class, or they can only come in like once a week or something. So I can't really. It would be harder to work like everything in the glove box, like I had been doing. And so I wanted some more air stable types of ligands, and I still wanted to see if we could do CH activation. And this is one of those things that, like, when you're looking through the literature, which I love to do, a dig back in the old literatures, you find things that you're like, oh, that's interesting, and you put that in your back pocket as you start to kind of develop your research proposals for your independent career. And so one of the things that I'd read about was that phosphites, which are a phosphorus with 3 OR type groups on them, they tend to be more air stable than phosphenes. Okay, that was good. So maybe I can do some phosphite chemistry. And then I saw this paper from 1992, it's only a couple pages. It's written on a typewriter. And it was from Yamakara, Fujita, and Shinoda in ChemLet. And they had shown that you can take cyclooctane, which is an alkane, and heat it with a phosphite platinum tin compound and get cyclooctene and hydrogen. Now, this is what's called acceptorless alkane dehydrogenation. This is thermodynamically uphill. Okay, and the way that it works is basically the Chatelier principle. You bubble nitrogen through, or you reflux it and drive off the hydrogen. And so hydrogenation, which is the reverse reaction, is thermodynamically favorable, and so that's much more common and easier to do. There are some iridium complexes that can do this type of reaction, but this was, I think, the only or one of the very few platinum examples I've seen. Vedernikov, I think, and Karen also had some examples of transfer dehydrogenation, where you make an H2 equivalent, but you use that to hydrogenate a different alkene. So I thought this was cool. And he had looked at just 2 phosphites, ethyl and methyl. And so these are turnover numbers over time. You can see it's slow. This is, again, not something that's going to be commercialized, but it's just, I thought it was interesting. And so it's something I wanted to study. So that became the kind of focus for my my work here at Depaul, right? Because phosphites are air stable, so they're easier to work with. You can buy them, in nice big bottles from all sorts of companies and keep them on the bench. They do still smell bad, like most phosphines, so that's always annoying, but you can just use bleach to clean that up. Okay, so a few things about phosphite ligands, right? So in addition to be sigma donating, just like they can bind, those PO bonds create a pi acceptor property, which is also known to be good for CH activation. So they're better pi acceptors, and that can lead to more electrophilic, like electron loving, which metal centers could lead to more CH activation. And there's been ways of measuring this. So Anthony Fernandez, when he was, I can't remember if he's a grad student or postdoc, but Anthony's now at Merrimack University, and he's part of Ionic Viper as well. He's shown that phosphites have much more pi acidity than other phosphines and stuff. And so it's shown that the methyl one has, this number is just a measure of pi acidity, and it's larger for these other ones. And so I wanted to see for these other guys, could we do CH activation? And so I should note, though, that there is a problem with triphenyl phosphite in that it can cyclometallate here really well, and that's well known for palladium, platinum. And so that's a problem because you don't want that. You want a CH activation to happen of your solvent, not of your ligand bound on. There's also the tin ligand, which is an interesting but complex problem too, because Shinoda said that if you have the tin ligands on there, which you can make by inserting tin 2 chloride into the platinum chloride bonds, it works better than if just the chloride, but the chloride still works. So to me, that was interesting. And the tin chlorides also tend to keep platinum in a higher oxidation state, so platinum 2 instead of decomposing to platinum 0. They could have several roles. It could be like just a good leaving group, right? It would come off and allow CH activation to happen at this site. It could act as an internal base, kind of like we've seen with the NH ligand in the PN complexes from my PhD. But so far, I haven't really looked at the tin chemistry yet because I wanted to say, okay, well, this works. Let's focus first on sorting out the chemistry of the phosphites. There's also another problem with phosphites, and that is that alkyophosphites can be de-alkylated in what's called a Michaelis-Arbuzov mechanism, especially when they're bound to metals. And this is, again, known chemistry. There's some great work in the 80s on this. But basically, the oxygen here, the PO bond stays together, but the oxygen is like a leaving group. And so the nucleophile can demethylate, for example, methyl phosphite, or deethylate ethyl phosphite. These are well-known chemistries. So that could lead to decomposition. That could be a problem. So again, I was thinking, well, you can't do SN2 chemistry on an aryl group. So maybe that would be one way of helping. Or maybe you can kind of tie it in some conformation where it can't do the SN2 chemistry. So that's what we were thinking about as we started working on this chemistry. So one of the first students in my lab started to work on this. His name was Jason Kosatarit. And so this work started when I started in 2013 at Depaul. And so we tried to make some bulkier phosphites. And this was one way that we were going to do it. Is there's actually this commercially available PN complex. These NP bonds are basic at the nitrogen and can be protonated off. And so we just added dimethylphenol excess, and we're just like, let's make the tri-aryl phosphite. Well, surprisingly, we didn't get there. We actually got the di-aryl phosphite selectively in good yield. And so he isolated it, he crystallized it. This was the first crystal structure from my independent work. And so it was nice that you could actually get this PN phosphoamidate from pretty selectively just by refluxing it in toluene. Now, if you want to get the three phenols on there, you can use PCl3 and just reflux it. People often use a base like triethylamine to do this chemistry, but you can just reflux the HCl off. You don't need it to add a base and just have more things to purify it from. Another thing we found was that these phosphites, sometimes they're kind of greasy when you isolate them as oils, but they crystallize nicely from cold acetonitrile. And that seemed to work pretty well for not just these phosphites, but also the corresponding platinum complexes and similar types of things. So that's been one of our kind of go-to crystallization tools. So now we've got some, and these aren't new phosphites, right? This one had not been reported before, but this is known in the literature. But now we've got some ligands. They're air stable. That's nice. Still keep them in the freezer just to make sure they don't decompose over time. And then we started to react these with platinum starting materials. Now, some chloride chemistry, it was a little annoying at first, and so we switched to the methyls, which we know methyls are stronger donors, and they tend to give cleaner reactions sometimes. And we found that we could. Now, again, I'm working with undergrads, and part of the issue is you don't want to have starting materials decompose on you. Well, this really commonly used dimethyl sulfide dimer, which is pretty much the platinum methyl starting material most people like to use, is actually fairly unstable. It decomposes over time in solution at room temperature. It's got a melting point of 86. Whereas the diethyl sulfide one, which is just a little bigger, is actually more stable in solution, and you can crystallize it in coal acetonitrile, or sorry, acetone. That's the solvent we like to use for this, but it has a higher melting point. So we use this for most of our chemistry for methyls, installing methyl groups. Again, this is air stable, fairly air stable. Over time, I think it decomposes in solution, but as a solid, it's fairly good. So let's make some compounds. All right, so we took this dimer, which you break apart. So you take one dimer and 4 ligands to make 2 equivalents of your square planar compound. This worked pretty well, quick, pretty high yields. And again, we can use NMR. And so the interesting thing here is that we see platinum methyls. Now, platinum phosphorus coupling is larger than you would see for phosphenes. So that tends to tell you that there's possibly a stronger platinum phosphorus bond, which is maybe good for stabilization. We made both of these complexes. They're air stable. You can make them on the bench, keep them in the vial. They're nice white powders. These methyl ligands, CH3 groups, were pretty broad in the NMR, and I think that's due to fluxionality. We didn't have a variable temperature NMR at the time, so I wasn't able to sort that out. That could be something we could go back and look at. But instead, we turned to our usual favorite thing of trying to grow crystals. And sure enough, we can get them crystal structures. So here's those 2 compounds. Now the platinum dimethyl is facing towards you. And so you've got the phosphorus here and the phosphorus here. This is the one with the nitrogens. You can see it's kind of, they're anti to each other. And then here's the one with the all oxygens. All right, so now let's see if we can do some CH activation. Oh wait, sorry. First, we tried to get even bulkier ligands, right? You can kind of see these are pretty bulky, kind of protecting the platinum pocket. And you're curious if we could get even more sterically hindered ligands on there. And so we made this diisopropyl phosphite, which again, you can make by taking diisopropyl phenol, which is actually propofol, the drug that is an anesthetic, and just refluxing it with PCl3. And you'll make this thing, which is an air stable ligand. Unfortunately, it's so bulky that you can only get one of them onto platinum. And so, if you take an NMR, as you're doing the reaction, you can see it form by phosphorus and proton NMR, but if you try to keep heating it with excess stuff, it just decomposes. And you get what's called platinum black or platinum mirror, where you get like a silver mirror, or you get platinum, like black junk at the bottom, basically on the side of your tubes. And you have to use aqua regia to clean that off because it doesn't dissolve in anything except strong oxidizing acid. So, we can't get bulkier than that, basically. And I've since put this ligand on gold, and so I have like a % buried volume and a cone angle, which is ridiculously bulky for this ligand. Okay, so let's try UCH activation. And so we had put these methyls on there to try to prevent cyclometallation. And what happens is cyclometallites the methyls. So both of the complexes, when they're heated, and they're actually, you can do this without doing it air-free. It works with just like air or even added water. You can add a drop of water in there and still get the product. It really likes to cyclometallate. You make this actual 6-membered ring, which is a fairly uncommon motif. I tried to look through SciFinder and couldn't find many examples of this at all. It's usually 5-membered cyclometallation rings. And so we observe this type of thing, and the coupling on these CHs is crazy because it's coupling to platinum, they're diastereotopic, and they couple to phosphorus. So it's kind of a mess. But we were able to confirm the CH activation of the ligand. And again, this is quick in 100 degrees. I didn't do full kinetics, but approximate half-lives are like 5 and 2 minutes, and they're just like done. And they're really stable. So we did it on a larger scale and got a crystal structure. And so here's the product. And so you can see there's your 6-membered ring. It's broken the CH bond on you've lost a methyl, and it's broken the CH bond on the ligand. So it's bitten itself as opposed to attacking solvent, which is what we wanted it to do. But we have been able to show that it's on very stable, air-stable types of complexes. You don't have to worry about, glove box work and things like that. So that's been cool. So that's kind of where we're at, or where we were at in terms of published work. What we're doing now is we're going back to look at smaller phosphites again. So we're exploring a variety of phosphites. Most of these complexes with platinum methyls and platinum chlorines are known in the literature, but they weren't well characterized. So we got lots of crystal structures of the various ones on here. So you can see here's methyl, ethyl, isopropyl. Each phosphite is tied back, right, to kind of prevent cyclometallation. And this one's a CF3 to see if we can get maybe further electron withdrawing, more electrophilicity on it. So these are the ones we've been exploring. And one of the things we found is that you can get some really interesting, undesirable but interesting de-alkylation. So when we were trying to make the chloride version with these ligands, we actually got de-alkylation, and we may have found this species. So there's a platinum in the middle here, and then there's what used to be a phosphite, but now one of the POC bonds is now a POH bond. And then each of these phosphines has lost one of their alkyl groups and has a POH, but then half of them are deprotonated. And so you have a hydrogen bonding between the POs. And I thought this was really cool and looks kind of like the cobalt-oxime motif for a well-known cobalt hydrogen evolution catalyst. So we might look at some of this type of reactivity later without the metals too. And it's neutral because you have one deprotonated oxygen on each side, and so that's platinum too. That was pretty cool. Now, we made these complexes and then heated them up to see if we could see reactivity with solvent. And so most of them are actually pretty darn stable, too stable. We're not seeing any CH activation. However, the triisopropyl phosphite decomposes pretty fast. And so what we think is happening is it actually cyclometallites the isopropyl group and then extrudes propylene, which you can see in the NMR tube if you keep it sealed, right? Propylene's a gas, but it goes into the headspace with a sealed J. Young style or glass flame sealed NMR tube. So you can see the propylene, and you can see that the methane is always methane H, never methane D. And so we're trying to now observe this intermediate, which we haven't quite been able to see yet, along the path to decomposition. But I think one of the lessons here is triisopropyl phosphites are not good if you're trying to do thermal reactivity with a metal that can do cyclometallation, because they'll just fall apart and make propylene. So we're still trying to get alkane CH activation. We have been able to observe some cyclooctane dehydrogenation with these systems, but I think that's going to be a future papers after we characterize and understand their reactivity at a kind of structural and electronic level. Then we'll do a bunch of refluxes with various alkanes and see if we can do CH activation and alkane dehydrogenation, like the Shinoda system originally showed in 1992, and see if that was a fluke or if that's something we can reproduce and do further. So again, this is not these projects have not gotten as further as my CO2 chemistry and bioinorganic chemistry, and that's just the way projects work sometimes. But we were able to, at Depaul here, we've been able to make a new phosphite ligand and use this commercially available starting material to make some interesting phosphite ligands. We can make air stable and water stable. They just stare at water and don't care. Complexes with these bulky aryl phosphites, and we can do the cyclometallation, which is CH activation, but not the kind we want. And then now we're looking at these smaller phosphite complexes and trying to characterize them and get their reactivity, and then see if we can try to get alkane dehydrogenation and not just cyclometallation or arene CH activation. So that was some of the platinum chemistry I've done in my career. There's other stuff that I've done too, but didn't have time to talk about that. So when I was at the University of Washington, Karen was my PhD advisor, and then I had lots of lab mates. These are the ones who are working on platinum chemistry with me. So Avery, Andy, Margaret, Wes, and Susan were all very, very helpful. And Nancy was the first grad student for Karen, but came back on a sabbatical, and we co-wrote a paper together. And then since being at Depaul, again, most of this work has been done with undergraduates. So Jason and Anthony were undergrads. Farah and Sean are undergrads. Sean is currently working on it. Edgar was a master's student who did some work on it as well. And then all of our crystallography stuff we send out to North Carolina State University. So all the crystal structures from Depaul were obtained there. So I grow a crystal and then mail it out to Roger. And so he's been a very valuable collaborator. And all the funding has been internal. So this has all been from Depaul's internal funding mechanisms. So with that, I think I'd like to thank you for your time and attention, and I'd be happy to answer any questions.
Excellent. Another fantastic talk. We do have time for a few questions, so we'll go ahead and jump into those. So the first one is how stable is the methyl peroxide species that you showed back on slide 31?
Yeah, so that was stable enough to get a crystal structure. So you can observe it in solution, and you can isolate it. So it's air stable. We did try oxidation chemistry with it, like out of phosphine, you get phosphine oxides, and some of that you could do, but it's pretty darn stable at room temperature. And so that's how we were able to get a crystal structure. You did it on, I think I did it on like a 50-ish milligram scale, rolled the vapor or pulled off the solvent and then grew a crystal out of something. I can't remember. Let's see, 31. Yeah, let's just pop back. So yeah, so now one thing we did notice is that if you did this reaction in CgCl2 and let it sit for a long time, you actually get the chloride here. But that's probably just from radical chemistry breaking apart the DCM.
Okay.
And so if you, for example, chloroform and DCM over time, if they don't have an inhibitor in them, you get little bits of HCl and some other stuff. So that's probably where that came from. Okay. But yeah, it's in benzene, it just sits there and stares at you.
Okay, all right, that's interesting. Yeah, because I always think of peroxides as being pretty unstable, but yeah, it's interesting that stays fairly stable as long as nothing acts on it.
Yeah.
So you mentioned this is a question I had that's sort of in reference to the original scheme that you talked about, but sort of applies more generally. So you talked about in I think it was Shilov.
Yep.
That scheme. So basically, the platinum 2 can do the activation, but then you have to have that platinum 4 oxidant to basically regenerate the catalyst. If I understood that correctly.
Sorry. Yep. There we go.
So is that something where you could replace the platinum 4 oxidant, like if you did electrochemical oxidation, let's say, so let's if you supported the platinum 2 species, let's assume that like it doesn't react in some other way that degrades it, but could you do something like that to?
Yeah, and I think people have looked at trying to do that either electrochemically or with like a copper oxygen. Right, so you can use O2 to quickly oxidize copper 1 to copper 2, and then that copper 2 could oxidize it. So yeah, I mean, lots of people have looked at replacing this oxidation stuff, and I know there's certainly stuff out there, but I don't know if it's been done electrochemically, because you need to be thermally. You need to have enough thermal energy to do the CH activation and the reductive elimination. So yeah, that would be an interesting idea. I don't know.
Okay, yeah, we can talk. We have a way that we can maybe do that. Okay, interesting. So I think it looks like that's all the questions that we've got. But again, great talk. It's super interesting. I learned a ton. I always do. When chemists present as an engineer, I'm just kind of sitting here just taking it all in. So super interesting work, and I really appreciate you coming on to present it.
Yep. Thank you. Thanks again. And look forward to seeing the other talks today and future talks at Open Science presentations.
Great. Appreciate it, man. Thank you.